Thank you for Mr. Chairman. Good afternoon, ladies and gentlemen. I'm Daisuke Sasaki from Kurume College, Fukuoka. Today, I'll be talking about influence of easy repair using plasma sintering and aluminum particles on fatigue crack growth. In this presentation, first, I'm going to talk about the motivation. Then, I will describe the details on the experimental facility used in the present work. After that, I will share with you some of the highlighted data. Finally, I will make a brief summary and talk about the future plans. In 1967, the Silver Bridge broke in the USA. The reason is decrepit. In Japan, after 20 years, more than 50% of buildings will be over 50 years old. But money, human resources, and time are not enough to repair the bridges. Additionally, in Japan, earthquakes have occurred frequently. So, in order to prolong fatigue life, easy repair is needed. On steel structure, friction stir welding, stop hole method, and welding repair are used to prolong fatigue life. On aluminum structure, friction stir welding is used. Certainly, these methods prolong fatigue life. They are useful. However, there is one problem which these cannot solve. What is it? It's a long crack over 10 centimeters. Then my question is, there is a long crack. When there is a long crack, how can we prolong fatigue life? My answer is making a sealer in a crack surface, inserting particles and sintering. This is our method. Fatigue crack propagate with opening process and crack closing process. Then displacements during crack opening and closing are corresponding to a crack propagation rate. Our method has two factors suppressing fatigue crack propagation. One is suppressing crack opening by addition between a sinter and a crack surface. Second is suppressing crack closing by inserting a sinter. We have studied this method from 2017, and we have succeeded in extending for fatigue life by 50% on steel. In this study, we have researched the effect of repair method with metal particles and plasma sintering on aluminum. Okay, I'm gonna talk about experimental method. We have used aluminum plate and aluminum powder and magnesium powder. Diameter of aluminum powder is 2 micrometer. Diameter of magnesium powder is 550 micrometer. Composition of these materials are like these. This is the repair condition. We have used pulse current sintering for repair. Load is 1 megapascal. Heating rate is 30 degrees per minute. Holding temperature is 450 degrees. Holding time is 5 minutes. We have used two kinds of powder. One is aluminum powder. The other is mixed powder. In mixed powder, magnesium is useful for increase of interface strength. This is fatigue test condition. Maximum load is 6,160 Newton. Minimum load is 3,380 Newton. Fatigue test is one-side swing test. Frequency is 1 Hz. Stress ratio is 0.05. After repair before fatigue test, some specimens are aged. aging condition is like this. This is experimental flow. We have conducted 6 tests. Without repair specimen with aluminum powder, repair specimen with mixed powder, repair aging specimen with aluminum powder, repair aging specimen with mixed powder, aging specimen. From now, I will share with you some of the highlight data. This is observation of simulated crack. The left figure is conceptual figures. The right figures are enlarged figures near simulated cracks. As we can see, we have succeeded in filling and sintering metal fine particles in the simulated crack. This is the result of fatigue test. Without repair specimen, broken at about 8,000 cycles. Repair reduces fatigue life by 70%, but aging after repair increases fatigue life by about 2,055%. And repair aging process extend fatigue life by 2%. This slide shows the relationship between the number of cycles and the crack growth rate. As we can see, on every specimen, crack insists until 500 cycles. Focus on repair specimens, both specimens broken at about 2,000 cycles. This result indicates that softening due to heating induced fatigue crack propagation. Focus on repair aging specimen, crack growth rate decreases after 6,000 cycles. This slide shows brittle fracture ratio. The left figure shows the fracture surface. The middle figure shows the enlarged fracture surface. The right graph shows the brittle fracture ratio. As we can see, repair increases brittle fracture ratio by 45.6%. Aging after repair decreases brittle fracture ratio by 43.9%. Striation width. We have observed striation on the fracture surface. The right graph shows the striation width on each specimen. As we can see, repair increases striation width, and aging after repair decreases striation width. These results indicate that heating during repair process induced softening, and aging after repair process recovers material hardness. And focused on repair aging specimens, it suggested that the sinter induces crack closure. This is summary. That's all. Thank you.